Right now we're going to talk about how geologic time is determined. When we talk about geologic time, it's really two different ways we describe it, but both of them are a way that we use to describe how old a rock is. So when we talk about geologic time, you have two choices. You have absolute age dating. Now the key to absolute age dating is that it gives an age of the rock in numerical years. For instance, you can see on the geologic time scale on the right of the screen here that you have ages going down. So for instance, the Mesozoic ends at 65.5 millions of years ago. So that's a numeric age versus relative age. With relative age dating, it gives the age of the rock with respect to another rock in the sequence. So in this case, you can say one rock is older or younger than the other. So looking at the Grand Canyon sequence, which we'll do a couple of times as we go through here, we could say that the Coconino sandstone is younger than the Redwall limestone. And the Redwall limestone is younger than the Bright Angel shale. Now, in that case, we don't know how much younger, just looking from here and using relative age dating, but we know it is younger. So what we're going to do is we're going to look at the tools for both of these and how these are determined. Alright, but when we're talking about figuring out how old Earth is, we really have to talk about two schools of thought in geology and in science in general. So our idea of dating how old Earth is really starts with catastrophism. So this is the kind of idea that all we see around us and the geologic time scale, or the whole column, and the landforms around us were formed basically in really big catastrophic events. Now obviously a lot of this goes back to biblical leanings where there are those people who may tell you that the Grand Canyon was all formed thanks to Noah's flood. So all of the rocks were deposited while the earth was flooded for 40 days, and then the canyon formed as the rocks drained away. So everything you see has to be formed by these great, big, huge ideas. And so this comes down to one of our most famous ways that we tell how old the earth is. Now, the man who brought us this kind of most famous way of dating the earth was a man named James Ussher. He was an Irish archbishop for the Church of Ireland. And what he did is he read the Bible, and he saw in the book of Genesis that it has a genealogy. So this person was born, and then they had this son, and then they lived for X number of years. And then this next person lived for X number of years. And then this next one lived for X number of years. So what he did is he sat down with his Bible, and he added all of those up. And what he decided was that based on the book of Genesis, counting all those years together, that the earth was formed around 6 p.m. on October 22nd, 4004 BC. And this has stood for quite a while. Like many Bibles, even now, if you open it up, that's what you read. And this is the date that you get used for a lot, that you hear from a lot of young Earth creationists. Now, in geology, we tend to think the Earth is much, much older than that. And I'll show you some examples of why, and I'll show you how we get the actual ages of things. It's a little bit more than 6,000 years. But this is sort of what stood for a very long time until a new school of thought came through. And this new school of thought, it was uniformitarianism. Now this is often described as the present is the key to the past. And this gentleman you see in the picture here, this is Hutton, and we'll talk about him a little bit more later. But Hutton was a gentleman who decided the earth was really old. And how uniformitarianism works is that if you look around at the processes happening right now around us, those are the same processes that have always happened on Earth. And those are the processes that have slowly formed everything we see around us. So that when you see a sequence of the rocks like the Grand Canyon, these, in the Grand Canyon, this right here, this ledge you see, this is the Redwall limestone. So that's formed in the bottom of the ocean. And you can go to the bottom of the ocean and you can see little layers of calcium carbonate being deposited. And you can measure how long that takes. It's, less than an inch a year. You can say, well, to get a 400-foot thick sequence, it takes X number of years to do it, right? So that's what he was looking at. Is Hutton said it takes so long for all these slow processes to happen that the Earth has to be old, and that everything we see forms from this really slow progression of everyday events. Now, really, where we are now is more leaning uniformitarianism, but a little catastrophism in there too, because we know big events like really large earth-changing volcanic eruptions happen. We know that really large impacts hit the Earth, and that can change everything. And that was something that wasn't even accepted widely until actually really, really recently, that the Earth even got hit by meteorites, which is actually quite fascinating. So if we go back to the very early days of figuring out how old things are, it was really started with relative age dating. So what we're going to look at now is some of the basic principles of relative age dating. How do we know the sequence in which rocks were formed? All right, so our first principle here is the principle of original horizontality. Now what this says is that rocks are originally deposited in nice flat horizontal layers. Now this is a picture in front of you from the coast of Essex in England, and hopefully what you can see is this is definitely not nice flat horizontal layers. So what this principle tells us is that it had to first be deposited nice and flat horizontal layers, and then afterwards they were tilted and folded. So this folding came second. This is actually a really famous location. This is called the Purbeck Group. These are limestones with really famous fossils from reptiles and early mammals from like the Jurassic era, the Jurassic period. Plesiosaurs are some fossils that actually are found in these rocks. But you can see how folded up they are. But they were originally horizontal. All right, we have the law of superposition. Now what superposition means is that the oldest rock is at the bottom. All right, so if we look at the Grand Canyon sequence again, the stuff at the bottom is the oldest, and it's younger as you go up. And that's why I could say earlier that the Coconino sandstone is younger than the Redwall limestone because it's above it. And the Redwall limestone is younger than the Bright Angel shale because it's above it. Now, obviously, there's always exceptions to this, and we'll look at some as we go through the semester, but as a first order, the oldest rock is always at the bottom, and that's probably what you should start with, the superposition, every time you're trying to determine a sequence. Now, if we stay here in the Grand Canyon, we can talk about the principle of lateral continuity. All right, that means that the rock layers initially extend laterally in all directions. It spreads out. It's just like if you take a bucket of sand and dump it on the ground. All those little sand grains are going to stretch as far as they possibly can. But in the Grand Canyon, there are buttes like these in front of you. So this is Brahma Butte and Zoroaster Butte. And on the top of it, of both of these, is Coconino sandstone. And that's the same rock you see in this nice, really light colored layer behind them. So what lateral continuity says is they were deposited originally in one solid layer, in one continuous layer. But when they're separated by a canyon or a valley, they originally were connected, but what's between them was eroded away. All right, so but they were continuous at one point. And that means it's the same rock and they're the same age. And we'll be looking at some examples of those as we go. Now, the principle of cross-cutting relationships. Now, this says if there's a geologic feature that cuts across other rocks, that cutting feature is younger than the rocks they cut across. All right? So this feature you see here, this is a dike. This is actually a really famous one in the bottom of the canyon again. We've got a lot of Grand Canyon examples here. So this is a basalt dike. So if we look at the little diagram on the right, a dike is an igneous rock. And what happened is there was some sort of crack in the rock and lava shot up through that crack. And then it solidified. And it's going to cut across all these different layers. All right, so what this tells us is that all those layers had to be there first so that there could be a crack in the rock so that the dike could squeeze through there. All right, so that's always the younger of the two. The other thing that'll do this as well are faults. So a fault is a crack in the rock on which you have movement. And a lot of times we can recognize that movement by offset layers. For instance, in this picture, you get a little idea of scale, but there's this dark kind of purpley layer. And this used to be one nice long continuous layer. And these lines that separate them, these are faults. So you can see here's a crack in the rock right through here, and this right side is actually dropped down. That's actually called a normal fault, and we'll talk about those when we get to structural geology. But you can see that that fault then has to be younger than the rocks. So we know this purple layer was already there. Well, actually, we know this bottom pink kind of layer was there, then this purple layer was deposited on top of it, and then this kind of orangey layer was deposited on top of it. Then this fault formed and everything moved last. This is a really interesting location because it is right across the highway from the entrance to Arches National Park in Utah. So these are a really famous sequence of faults. So faults and dikes are the two things that are going to be included in this cross-cutting relationships. But the fault and the dike are always younger than the rocks they cut across. We also have this principle of baked contacts. And this comes back to igneous rocks again. So a pluton, this is another type of igneous intrusion. So it's similar to a dike except it's spread out. So it's not filling one little crack, it's filling out a big area. Alright, and this pluton is really hot. And it's it's squeezing up into layers that are cold. So when that hot rock hits those cold rocks, it heats them up and it bakes them. In class and diagrams, you'll be able to recognize it by this kind of shaded area, or in lab there's like a stipple area around it. We'll try to make it obvious for you. It's not always so easy to see in the real world. So here's a sill. So a sill is actually pretty similar to a dike, except where a dike cuts across layers, a sill actually fills in between them. Alright, and we'll look at some examples in class of sills too. But this bake layer, this kind of weird soft stuff right up here, right above it, that's all an area that was actually baked by that sill and heated up. And now it's turned into a type of metamorphic rock versus, looks like more sedimentary rock right on top. So the baked contact tells you that to be heated up, these rocks had to be here first. So the baked contact bakes older rocks thanks to the younger plutons. Now inclusion is a little piece of rock that's included in or incorporated into another rock. And there's two examples of these here. On the left is an igneous inclusion. So there is a dark piece of igneous rock inside a lighter color of igneous rock. On the right is, well, currently it's a metamorphic rock, but this was a type of sedimentary rock where you have little round pebbles that are all stuck together that are part of a bigger rock. Now what the principle of inclusions tell us is that the inclusion is always older than the rock that contains it. Alright, so in order to form this conglomerate, you had to form all these rocks, and then they had to weather into these little pebbles, and then we could put it all together as one big conglomerate. So this rock right here is older than the whole. This dark area, this dark in here is older than this big one. And in class, we've looked at the mantle xenoliths, the lovely chunks of peridotite inside of basalt. It's the same thing. So the peridotites are going to be older than the basalt that they're in. All right, those are big ones. There's a couple other things that we talk about quite a bit in terms of these. This is William Smith. You have this man to thank every time you're looking at geologic maps in class, because he made the very first geologic map ever created. It was a map of England, which is pretty cool. Now, he worked for companies who were building canals. Before there was a railroad, in England they would build canals. They'd dig out these big canals and run like fake rivers through it, and they'd take goods up and down these canals in boats. And he was part of the team that was helping do those. And what he saw is, as they would dig the canals out, he would hop down and look at the rocks. And what he found was, he found the same fossils every time. And he'd find, for instance, he'd find this clam fossil. And every time he found the clam fossil, he always found this kind of pointy shell under it. And every time that he found that pointy shell, there was always these coiled ammonites under there. And under those coiled ammonites, he'd always find brachiopods. And under the brachiopods, he'd always find graptolites, which is what this is. And under that, he would always find trilobites. He never found trilobites on top of ammonites. He never found graptolites on top of clams. He never found clams under the brachiopods. They always happened in the same order. And he called this faunal succession. And what that means is there are certain fossils we call index fossils. And it's a fossil that happened, it was an organism that lived pretty much worldwide, but didn't live very long. And what that means is, anywhere you go in the world, if you could find that fossil, you know exactly how old it is because of those rocks that it formed in. So a lot of times we can use fossils to do this too. Now, rocks aren't always in big continuous sequences, even though they start that way thanks to lateral continuity, right? And so what we can do is we can correlate rock units. So you can have rocks in one location that were continuous with rocks in another location at some point. And what we can do is we can figure out where those line up. And sometimes that means you can figure out if rocks are missing, or you can figure out if, hey, there was maybe a beach. That's what these little dots mean, is a sandstone. So maybe this was a sandstone that was formed at a beach, and since it doesn't go all the way over here, maybe that beach didn't extend that far. But this is really important to figure out how rocks in different areas line up. One of the cool things we can do is, when the rocks along the Colorado Plateau, we can correlate them, and we get a really long history of the area. So the oldest rocks are going to be found at the bottom of the Grand Canyon. These rocks, like the Vishnu schist, are billions of years old, and they get younger and younger and younger as you go up. Now, as you drive north, what's going to happen is you're going to have the Kaibab limestone, and on top of that, you have the Moenkopi Formation. It's a real nice dark red rock. You may have even seen this driving around Flagstaff. The really dark, flaky red rocks just north of Flagstaff are the Moenkopi. Well, if you go on up into Zion in Utah, what we find is the Kaibab limestone is at the very bottom of the rocks there. You've got the Moenkopi on top of that, then the Chinle. Now, the Chinle Formation is really famous because this is where you find the painted desert and petrified wood of the petrified forest. All right, and on top of all of that is the Navajo Sandstone. Well, if you go on even further up into Bryce Canyon, the Navajo Sandstone is at the bottom, all the way up to the Wasatch Formation on top. So we can actually know that the Bryce Canyon is younger than the rocks of the Grand Canyon, even though they don't have any rocks in common, but because we can correlate them through Zion too, which is pretty awesome. Now, a lot of what we've been talking about so far has been rocks forming and the order they form in. But rocks aren't forming all around us constantly. If we walk outside right now here in Mesa, there's very few rock layers forming because there's very little being deposited. What's happening is things are eroding away. There are some young rocks that are eroding away. There are some new rocks that are eroding away. And this gets preserved in the rock history too. And in the rock record, these are called unconformities. So an unconformity is a boundary surface between two surfaces or two units. It represents a period of erosion or sometimes even just non-deposition. So you just didn't have anything being deposited at that time. So I'm going to show you some examples of some unconformities. And I'll show you diagrams and how they form, and then I'll show you what they really look like. So an angular unconformity, you've got layers that are above and below the unconformity that have different orientations. So for instance, we're going to start with nice flat horizontal rocks, just like we're supposed to, thanks to the law of original horizontality. But then something's going to happen. We're going to tilt those rocks over. This could be two plates running into each other and folding the rocks and making mountains. This is not uncommon. All right, so we're going to tilt them over. Then we're going to erode them. There's your erosional surface. And sometimes you can tell when things have been eroded because that erosional surface is sort of irregular. Sometimes you can see river channels in it. Sometimes there's little pockets of soil left behind. But so you've got these tilted rocks with lots of stuff being eroded away. This is even sort of like the head of the Camelback Mountain. That's what these rocks look like here. Well, then the erosion stops and maybe the sea level rises, and now we're putting more rocks on top of it. And then sea level drops again and we start eroding again. And so this is our current situation. So you have flat-lying limestone. That's what this brick pattern means. If you want to check what these patterns mean, you actually have a page in your MCC custom edition of the textbook that has these patterns to show you what they mean. They're also in your lab book. All right, but you have these pretty flat-lying limestone on top of not so flat-lying limestone. And since this surface right here, that is your unconformity, normally it's going to be represented by a kind of a wiggly line or a dark line in cross sections like this. But you can see the rocks above are definitely at a different orientation than the rocks below. So that is an angular unconformity because they meet at an angle. So this is Sicker Point. We talked about Hutton earlier, at least I showed you a picture of him. This is Sicker Point. It's a point along the coast of Scotland. Now, Hutton was trying to convince some of his buddies that the Earth was really old. So he put them in a boat, and they went up the rough seas of the coast of Scotland until he found this point. And he said, if you look, all the rocks down below on the bottom of this cliff, those are all tilted over and they're almost vertical. Now these are all mudstone. And if you look, every time it floods and it deposits mud, it's a teeny tiny layer. Which means to deposit all this mud would take a really long time. But then something had to tilt it over slowly without breaking the rocks. And then they had to all weather down because you can see that erosional surface right through here. But then more mud got deposited on top of it, and all of that was tilted over again, just not so much because you can see those are actually at an angle. And going through this was how he convinced his friends that were on the boat with him. It was friends and scientists and mathematicians that he had. And he actually convinced them that the Earth was actually really old that way. If you're into these things, I always suggest these kind of things. There's actually a book on Hutton. It's called The Man Who Found Time. And it's a biography of him and how he came to putting all this together. He's one of the first people who suggested all of our relative age dating principles. All right. Type of unconformity number 2. These form in the exact same way as the angular unconformity. The only difference is that nothing gets tilted. Alright, so in this case you have parallel layers that are going to separate erosional planes. So a disconformity is where the boundary between two horizontal layers represents that disruption in deposition or an erosional surface. Alright, so you can see here we've got layers and layers. The bottom is a mudstone, then there's a sandstone, and a limestone with a lot of chert deposited, all looks like underwater. And then we erode. Now notice that purple layer is completely gone now. It's just not there anymore. Alright, you've got an erosional surface there. Now we're going to put more stuff on top of it. And then there is your unconformity. Now, this is sometimes really hard to actually recognize. Because if all the rocks are just horizontal stacked on top of each other, sometimes that's just how they form. So it's really important to be able to recognize either like signs of erosion, things like soils in there or river channels, or to be able to recognize the fossils. So if you go like Hutton's fossils, if you go from one of those trilobites that are really old and the rocks right above it have the clams that are really young, you know there's stuff missing in between. So here's an example of a disconformity in real life. And you can see, unless you knew erosion happened right here, you may never be able to recognize that as missing time. But down here you've got layers and layers of, looks like probably limestone, and on top layers of sandstone. But those are parallel to each other. And last but not least, we have a nonconformity. And in a nonconformity, you've got layers of sedimentary rocks that overlay older, either intrusive igneous or metamorphic rocks. And these we call crystalline rocks. And that's because these rocks form at depth. All right, so you have you got layers of rocks, you got an intrusion of magma. Now we know this magma is younger than the layers of rocks because you see that little red halo? That's your bake zone. So we know the magma came second. Now for so it looks like cake sprinkles, right? This means it's a granite. Now we know granite forms deep underground. It's got real big crystals. It forms really slowly. So you're looking like 10 to 15 miles deep to be able to form granites. All right, so we know it was really, really deep when it cooled. But what happens to this is over time you get uplift. So you have to have uplift to get these up to the surface. So those were uplifted to where the surface is. All those rocks that used to be on top of it have eroded down. That's how you get granite at the surface. So this is like the hump of Camelback Mountain. It's made of granites. Or South Mountain. South Mountain has a lot of granites on it too. Those rocks formed really deep underground. Now you've got those rocks that formed really deep underground, but now more rocks get put on top of it. All right, now notice now, we're going to finish that off, and you can see where that nonconformity, that unconformity surface is. Now notice, we're back to granite beneath layers of rocks, just like we started with. We know the granite is older at this point because of these guys. There's inclusions of granite in those rocks above it, so we know the granite has to be older. Alright, the key to this one is to be able to recognize the fact they have crystalline rocks down there. That means nice big interlocking crystals. One of the ways to recognize it just in a cross section is notice these rocks don't have any layers. Alright, it's one big blob of rocks. The other way is to actually look at the patterns and be able to recognize the rocks there. All right, so rocks that are crystalline that are commonly going to be underneath those nonconformities. It could be granites, it could be diorite, or gabbro. Now these three rocks are your kind of big classes of intrusive igneous rocks. So these are rocks that form underground. We'll talk a lot more about what that means really when we get to igneous rocks, but just know these have to form deep, deep underground. You can also have metamorphic rocks like a schist, like a gneiss. That's how that was pronounced. You can see those stripes of color there. A quartzite or marble. So any of these can be beneath a nonconformity. So if you want to see an example of a nonconformity, we go back to the Grand Canyon. It's a perfect example of a lot of these, isn't it? So if you look here, you've got the inner gorge. So this is the Vishnu schist. It's got streaks of dikes of the Zoroaster granite. All of this is ancient rocks, billions of years old. But you notice there's no layers at all. But on top of it are these lovely layers again. Alright, so that nonconformity is right where these dark basement rocks touch these lighter layered rocks. So again, you're looking for rocks that are massive without layers with layered rocks on top of them. It's one of the easier ways to recognize those nonconformities. So, we've talked about how to tell the order in which rocks form. We've talked about how to recognize how rocks erode. And now we're going to look at how we tell exactly how old a rock is. So this is our absolute age dating. So we're going to use quite a few terms in here. All right. So the process of determining a numerical age of rocks is known as radiometric dating, or according to your textbook, the more preferred term is isotopic dating. And I also tend to use the term absolute dating. So these all mean basically the same thing. All right, and the key here is we could say all the dinosaurs died at the end of the Cretaceous period. What that means is when all the dinosaur fossils stopped, everything younger than that was not Cretaceous in age. All right, that's basically how we define the Cretaceous period, is because we find certain dinosaur fossils, like everybody's favorite friend, the Tyrannosaurus Rex. Or we could say that the dinosaurs all died right at 65.5 million years ago. And because we put a number with it, we know that has to be an isotopic date. Now, this has only been an option for us since about the 1950s. And the key to this is radiation. All right? And so what we know is there are certain isotopes that are unstable. And unstable isotopes undergo radioactive decay to become more stable. All right, so in this case, that unstable isotope we call the parent isotope. That one's unstable. It's too big, it's too heavy, something's going wrong. It undergoes radioactive decay, gives off heat, gives off all sorts of nasty stuff sometimes. And that more stable isotope that you get out of it is called the daughter. So we're going to use that parent and daughter term quite a bit here. Now, the cool thing about this is that it happens at a fairly regular rate. We know how long it takes for a parent isotope to decay to a daughter isotope, at least kind of on average. And this is called the half-life. So the half-life is the time it takes for half of the radioisotopic isotope to decay. So this is the time, this is how long it takes to get half of the parents left. All right, so when you start, you've got all parents. So this is a graph of the parent isotope. So in this case, when you started, you had 16 parent isotopes. After one half-life, you have 8 parent isotopes. After 2 half-lives, you have 4. After 3 half-lives, you have 2. After 4 half-lives, you have 1. So it's an exponential decay, which means that those numbers decay really, really fast. Now the key here is you always have the same total number of isotopes. So for instance, you always have 16 isotopes. The green in this case is the parent and the blue is the daughter. Now, one of our big assumptions for doing isotopic dating is that you have to assume that when the rock formed, or when your mineral formed, there was only parent isotopes and there were no daughter isotopes. And depending on the isotope, that could be a pretty easy one to assume. At one half-life, you can see there's half as many of the parent isotopes, but the other half has turned into daughters. After another half-life, you've got half as many again, but the rest are daughters. So at each stage, you have the exact same number of isotopes. That doesn't change. So there's another way of looking at it. So here is T equals 0. So this is when the rock forms, and you've got all parent. At T equals 1 half-life, you've got half parent and half daughter. At 2 half-lives, you've got a fourth of it is parents, and the rest is daughter. At 3, only an eighth is parents. And after 4, you've got 1/16 that's parents. All you got to do is divide by 2 each time, so it's not too bad. The other big thing you have to assume is that it's a closed system, and that's why we have the same number of isotopes the whole time. Right? So if it's a closed system, there's no daughters when it forms. There's no parents coming in afterwards. There's no parents leaving. All right, so what you start with is what you keep. So that's assuming a closed system is why we have the same number of isotopes each time. Now, not every isotope is unstable. So you have to have an unstable isotope to be able to do this. And you have to have one that decays into a rather stable daughter that we can measure. So some really common ones that we use in geology is strontium, We have samarium-147, which decays to neodymium-143. Right, and those are just ways we indicate the isotopes. So when that decays, the half-life is 106 billion years. Now let's think about that. Our entire universe, as we know it, is about 13 billion years, which means we've still got a whole lot of that samarium left and not a whole lot of that neodymium. All right? So you can only really date really, really old things very easily with this. Other ones are rubidium strontium or uranium-238 that decays to lead-206. This one has a half-life of about the age of the Earth, so we can date some of the older things on Earth. Potassium-argon dating is pretty common. I actually worked during a internship that I had at NASA Johnson Space Center. The guy who was my mentor for it, the gentleman, he actually did potassium-argon dating on meteorites to figure out how old they are. So that's a pretty cool thing. Or uranium-235. So uranium has a number of different radioactive isotopes. Now you've probably heard of this before. And you've heard of carbon dating. So carbon-14, which is created inside living organisms, decays to carbon-12 when that organism dies. So as long as you're alive, you're creating new carbon-14 in your body. But as soon as you die, your body quits creating that and everything starts to decay. And that's why we can date those pretty easily. The problem with it is it only has a half-life of 5,730 years. So it's much, much shorter than the rest of these. What that means is you can't date very old things with carbon dating. So we don't do carbon dating on dinosaurs, but we do use it a lot in archaeology because you can date things within human time spans fairly easily this way. Now we know the Earth is about 4.5 billion years old, and we can get some dates of materials to help us get there. So on the left is a zircon crystal, so that is a type of mineral. And it has been dated using isotopic dating to 4.404 plus or minus 8 gigaannum. So that GeA means billions of years. That plus or minus 8 tells you the uncertainty, which is always a good thing to know from scientists, is how certain that number is. So that means it could be 14.412. It could be 14.396. How do you do the math in my head there? All right, so you could add 8 or subtract 8 to the number to tell you just how well they know that. On the right is a lunar zircon. The moon and the Earth solidified at the same time because the moon was formed from an impacting event into the Earth. So the Earth is just a little bit older than the moon, but the lunar rocks haven't changed as much as the Earth ones are. So this is a lunar zircon that was collected during the Apollo 17 mission, and that was the very last one. It also was the only geologist to walk on the moon, Jack Schmitt, that collected this. And that was dated to 14.417 gigaannum. Now meteorites are even older than the Earth. The meteorites, these represent the very first material that clumped together, particularly these carbonaceous chondrites. And so this is actually a meteorite that was studied at ASU, and they determined, using lead-207 to lead-206 isotopes, that the age of this here meteorite was 4.5682 billion years old. So that sucker was floating around the solar system before the Earth was even formed, which is pretty amazing. Now, is this foolproof? No, nothing in science is foolproof. So not all rocks can be dated. All right, so there's some issues that come along with it. So if your rock doesn't have those radioactive isotopes in it, So you're looking for minerals that have these. And these are, in the chart here lists the types of minerals that do have it. Maybe you don't have garnets or micas or feldspars or hornblends. It's actually really common to not have those. So if you don't have a mineral that has a radioactive element, you can't use this on there. Sedimentary rocks don't work very well at all either. So here's a conglomerate. So remember we talked about inclusions earlier. So if you were to try to date this rock, if you dated this little clast, you'd get the date of when that rock formed, or you get the date of when this rock formed, or this rock, or this rock, or this rock. You'd get hundreds of different dates because it tells you where those original rocks formed, not when the whole thing formed. But that's okay, because at this point what you do is you take the radiometric dates that you do know, and then you can use relative age dating to pinpoint when some of those other rocks, how old those other rocks are. All right, so rocks that work usually really well for radiometric dating are igneous rocks, granites and diorites and gabbros, those intrusive rocks, or volcanics like sometimes basalt, like rhyolites, and like andesite. Those are things we can date fairly easily. And so those are what we're going to look at in terms of being able to date the rocks. Now what this means is we put all this together and we get the geologic time scale. This is our calendar. It's broken up into eras, periods, and epochs. So like any calendar, this is like your years, your months, your weeks. So these are just smaller and smaller ways to break these up. And they all have big things in common. So Paleozoic. Paleo means ancient, zoic means life, so ancient life. Meso means middle, that means middle life. And Ceno means recent, so recent life. Alright, and each of these ends when a lot of animals died, basically. So this part of the chart was built thanks to relative dating. All right, so Paleozoic ends at the end of the Permian, 251 million years ago. 95% of life on Earth went extinct. We lost major animal groups then. The one everybody knows is when the Mesozoic ends with the extinction of the dinosaurs. And of course, we are in the Cenozoic right now, but this end of the Cenozoic will happen eventually. Now, most of these are based on kind of the major life, right? So the Paleozoic ends when the major life forms died. The Mesozoic ends with the dinosaurs all dying off. You know what the most important life form for the Cenozoic is? That would be us. So the Cenozoic will end with the extinction probably of humans. Of course, only the aliens will be around to see it, right? And the roaches. It's a weird way to think about it, but we are just another step on this geologic time scale. I always joke that humans are the perfect index fossil because we're spread throughout the whole world and we probably won't be here too long. So someday some alien critter is going to figure out every time they find human remains and evidence of humans, they'll know exactly how old those rocks are. So of course these were all put in order first. What we're able to do now is add these ages. So we know everything died 251 million years ago thanks to doing this isometric or isotopic age dating on the rocks of that age. And you'll be using the time scale in lab quite a bit. And we'll talk about, when we talk about rocks, how old they are. We generally refer to the geologic period versus the numerical age just because at this point those numbers are understood. All right, so the key now is to take what you've learned and to apply it. So what you'll want to be able to do is, given a sequence of rocks, be able to put them in order and tell me which came first and which came last. And that's a lot of fun because it's sort of like a puzzle.